CSS that we will dive down a little deeper into Spark. First, there's always some review of what we learned yesterday. So the most important concepts of Spark are transformations and actions. The transformations are performed with, for example, level operation, and actions are performed, for example, with a release operation. And the transformations only define the level function, so it's a pure transformation. And if you actually import a transformation to the Spark driver, then the Spark driver generally will execute that, and then at the end you get execution. So it's release iteration, and actions define a method which actually starts the block on the cluster, so every action corresponds to a single block. And the actions are methods which only be evaluated by performing actual actions. The cluster is run as soon as the execution of this driver program encounters the first action, not before that. And if this happens, then what has been built up in the execution graph until that action will be executed during the action itself, of course. When we talk a bit about important transformations, I guess the most important ones are, of course, map and map partitions, which is actually only called once per partition. So that's the difference between maps. So map is called once per item. So if you have like 5 partitions, so it's 10 items, then that partition is only called 5 times, and that is called 50 times. Also, this is important if you are able to for a sample, because most of the time you don't want cluster to run on the entire data set, because we are talking about big data, so it's hard to use too many data to do this. The reasonable time, all of the time, for debugging the testing practices. And then, of course, you have all these nice methods for adding units, intersections, and so on. And also moving. Also, repartition is important. That we redistribute the data, and this can be necessary if we have created some kind of imbalance across the partitions. So that if you don't rebalance it, then it will happen that some nodes of the cluster will be done very soon, and others will still have to do a lot of work because they have a lot bigger partitions. So in this case, repartition might be necessary. But of course, it's creates shuffling, so you know. And then, also we talk about important actions. First and foremost, of course, the use function is an action. The function must be commutative and associative, so it must be commutative because the order of the operands can be changed by the optimization later. So Spark will decide to rearrange the graph if it gives it a better idea. And you can actually collect all the items in an RDB. And of course, it's dangerous because it's returning all the elements of the entire RDB. If you actually want to inspect in the debugger what's inside, you actually have to do this, because RDBs themselves, they're just an abstraction, so they don't contain the data in the debugger. But of course, if you run a collect, then it will collect all the data from the cluster and send it to the driver. The same goes for count actually, because in order to count something, you need to collect it first. Also, you're aware that if you're using such something like for each, you need to update an accumulator. So counting accumulators is a better idea, because it's not consistent across the entire cluster. Then we talk a little bit about RDB persistence. So Spark can actually persist RDBs so that intermediate results are not lost. Otherwise, they will all be discarded once an action has been performed. And there are several persistence levels you can choose from. If you choose cached, then it will just use the default storage level, which is only cache on the memory. But you can also decide to cache in onto disk or memory and disk. But this is usually only a good idea if recalculating the data is more expensive than storing it. Now I want to, let's go into actually running Spark. So these are the available coordinates for Spark. I guess it is the most recent version. There may be a more recent version which is at a beta stage, so generally general advice for me, so be careful with beta or alpha versions because, well, I mean, if of course it's a decision of the developers to mark something as a beta version, but if the developers believe that this version isn't stable, you shouldn't believe it is, right? So because the developer probably know the software better than we do. So never use beta software for production. And there may always be some bugs which you not counting on. Of course, there can also be bugs here, like there are, you know, some, but better versions of course have much more bugs usually. So this is the most recent version, which is even stable, I guess. Also for Spark SQL, it's a separate model. So you can use these data coordinates to access Spark SQL. The models always have the same version as the core, if the interfaces are compatible. If you wonder what this is, so this is just the version of the recording compilation. So I guess 2.12 is also available, but usually because Scala has actually different, so the binary format of Scala has changed from 2.12 to 2.13, so there are different versions for different versions of Scala. But I guess this is the most recent version. So, then this is an example for a Maven configuration. Actually, it's pretty straightforward. So just be aware that the Java version which the current Spark version is compatible with is at the most the 21, not the most recent Java version. So could be 21, also 17 or 11, but don't use the Java version newer than 21. It may work a little, but not always. So at least the developers don't guarantee that it will work, so be careful with that. Actually, they only guarantee the full compatibility with Java 11. Well, I didn't find anything that doesn't work with 21, so it seems to work. But in general, it's lagging a bit behind the most recent version of Java. Then this is an example COM file for Maven. So this is dependencies. So we have to should use the scope compile for both COM and SQL. General advice. So be aware that sometimes if they're using cloud providers, then they may already have a redeployed version of Spark. So in this case, you should use the scope provided because otherwise you are bringing your own version of Spark to the cluster and to the cloud. And that can be a problem because then, I mean, the environment has been configured for their version, so the version might differ in some regard with your version. So if you mix it up, you will get some very weird errors because there may be some incompatibility between the interfaces. So if there is a version provided by a cloud provider, then use this version and don't compile your own Spark version into your fetch binary, so into the fetch answer. So because otherwise you might run into problems. Of course, if you just compiling it client for testing purposes, you can just use this code compile. This is also important. So Yeah, there's actually a bug which hasn't completely been fixed right now, or yeah, it's not directly a bug, but it's more a problem caused by a change in the way the reflection is implemented in Java. So they changed the reflection API in a way to be more secure in more recent Java versions, which rendered it incompatible with the way Spark behaves. And the developers of Spark didn't really want or run everywhere at all to actually fix this. Maybe because you can actually circumvent this by adding these switches. So if you can place this to the VM settings of the IDE. So be careful if you're using IntelliJ. These are actually the VM settings. You need to mark them with a checkbox that are visible in the properties immediately. So select VM settings because these are settings to the VM, not to your application. And basically what they do is they disable this additional protection of the reflection for all the classes, and then it works again. So if it works without it, it might still make problems at some later stage of execution. So I recommend to do this. If you're interested in why this is, you can find this in the Stack Overflow discussion. I mean, basically, I guess the developers did not fix it because it was finished at this, but still it's some kind of, a bit convoluted, whatever. So add this to the run configuration of the VM settings. Then if you want to run Spark on Windows, there's a native Hadoop component required to access the local file system. So native means it's compiled for Win32, so the Windows API. In order to use this, you can download the binaries for the Hadoop version 3.3.5 because they're actually compatible with both Spark 3.5.3 and 4.1. So the most recent Spark version. You can download them from here. Actually, they are not provided by the Apache Foundation, but only by some private maintainers who do this on their own. So, of course, there are different builds available, and I guess this one should be trustworthy. I mean, as always, be careful with downloading some stuff on the internet. People you don't know. But in this case, there is also a link from the Apache homepage on. So this should be fine. And then we need to set a home environment variable to a path that points to the lineages. So the variable needs to point to a path where there is another subdirectory called bin. And within this subdirectory called bin, there is the lineages access and the Hadoop DLL. So which can be found here, right? So you can download it. So set this environment variable to this path where this bin subdirectory is located. Why? Because it's required to manage the POSIX file system access rights, which HDFS is requesting from the local file system. So on Linux, this is just right out of the box because it has a POSIX compliant file system, but not on Windows. So we need some kind of wrapper, which is what these Winutils are doing. As I said, so the builds are not perfectly divided. So, of course, you can use different builds from other maintainers. I don't know. These work for me, so I guess it's safe to use them. Then this is a pretty simple Spark program, very basic. Just to show you how you can run it on the local machine. And you can see here that we just we have the main method, and then we are using the Spark session object, and we test a builder, and the builder allows us to create a session. We just set the name and the config, and as I said, for the config, we can use the local key profile, which means it's running on a local machine with exactly 2 threads. And then and create a context out of the session. And now we have a context, so a context of everything of Spark. And now we are creating an RDB using, of course, a method from the context. In this case, it's just a method called text file, which reads like this text file into an RDB. And then, for example, we can do something with the RDB like this. So we are partitioning it on 4 lines and 3 partitions. I'm not sure if this is necessary depending on the default available part, but after we do this, we have exactly the partitions. Then we are mapping it to the each value, then mapping it to square, and then actually adding it up. So pretty simple, as I said. And yeah, I want to show you that it actually runs. Okay, so you see this is the same program. And yeah, if you want to see what our text file is, so it's this, right? So it's just CFC. And yeah, now we can actually run this. And as you can see, it's not running very fast, so we don't do the same without Spark, we would be finished by now. So, of course, Spark has a lot of overhead, so it's not really something you should use for things which can perfectly run on a single client. Yeah, and now we see that it's logging a lot of stuff. And finally, it's actually see here, so we have the output of the program. And you can see that it actually exited with exit code 0, so everything was fine. You can also see some other stuff here, like yeah, it tells us what version is running on, something about the Java version, some stuff from the security manager. Yeah, I will later talk about this. So yeah, some security considerations for Spark, and also some status reports from the different components of Spark, like the executors, the schedulers. Yeah, and you also see that there is a web UI, and we'll also talk about this later, which you can use to monitor what Spark is doing. It's terminated once the entire driver process is terminated. And then you can see it's actually being executed. What you can also see is that this execution took roughly like 2 seconds, which is of course, yeah, I mean it's pretty much right for, yeah, I mean basically adding up for numbers would be like less than 1 millisecond. That's no problem. So of course, yeah, there is lots of overhead involved in actually running this entire system. But of course, yeah, it's not aimed for this kind of application. So you can see it's actually real, so you can actually run it, right? Okay, so yeah, we had this before, so but just a small reminder. So the general architecture is that we have this context, and we have this cluster manager. And actually the jar file, so the actual code, is being transferred directly to the executors. So this is not done by the cluster manager. But the cluster manager is distributing the tasks, but of course the cluster manager expects that you already have Spark up and running here on the executors. Otherwise it won't have a counterpart to talk to. So the code must be present on every node, and yeah, depending on the way it's deployed, you might need to do this manually or not. Yeah, I'll talk a lot about these directed acyclic graphs. So yeah, what's directed acyclic graph? As I said, it's a graph without cycles. That's why it's called acyclic. And in this case, the nodes represent the RDBs. And the edges represent the transformations. And this pretty straightforward. So that's the application model of Spark. So we have this driver. The driver is the kind of main problem. And once the driver encounters an action, it should adopt. And each job consists of one or more stages. And the jobs are run in parallel. So the driver can run more than one job. The jobs can be run in parallel, they don't have to. It depends on the way of scheduling you have to configure. I will also talk about this later. But basically the jobs are independent from each other. And depends on the way your Spark environment is configured if the jobs will be run separate concurrently or not. But a single job consists of one or more stages, and the stages are always sequential. So they run sequentially. And that is because they express some kind of dependency. So stage B requires stage A to be completed, and stage C requires stage B to be completed, and so on. So that's why it must be executed in a sequence and not concurrently. Every stage consists of one or more tasks. And the tasks always run in parallel. So it's not something you, well, strictly speaking, you can configure, but it wouldn't make any sense in order to restrict the task at the time. So usually the tasks are separate threads. And the task is the smallest log package of an executor. So every task is assigned a single partition. And so if you run the job has multiple stages, and each stage will be split up in different tasks. And each task gets a separate partition, and then all partitions are processed in parallel by the executor. So like this. So if you look into a job here, so this here is the job. And in the job we may have like 2 stages. So first we need to completely execute stage 1, and then we can move to stage 2. And stage 1 might consist of like 3 tasks, which are processed in parallel, and after they have all been processed, so we aware that it may mean that one task may take longer than others. So in this case, the entire framework is to wait until the last task is finished in order to move to the next stage, because the results of all tasks are required to start with the next stage. In the next slide we'll see why this is. So then it will proceed to the next stage, also decomposed into various tasks. And finally, if they are all done, we're done with the job. And if there's a new action, we can proceed to the next job. And as I said, the jobs themselves may be run in parallel, but also may be run sequentially. It depends on the Spark configuration. Because in theory, they are independent of each other. Now there are 2 basic types of transformations, and these are called narrow and wide transformations. And it's a very important difference, because the narrow transformations, they are basically some kind of bijections. So use the injective, so that means you don't need any shuffling. An example for this is a simple map, or a filter, or a union. They're always mapped to a single stage. So if you have only doing narrow transformations, Spark will only create a job with a single stage, no more than that. And each input partition creates only one output partition. So that's the definition of narrow transformation. That we have this one-on-one relationship, that each input partition will only map to one output partition, and not more than that. And of course, the opposite in some regard are the wide transformations. Examples for this are reduced by key, group by key, or distinct. And in this case, we need shuffling. That means, we need to retrieve data from other partitions as well to actually perform this operation. So this means, of course, that we are doing shuffling, so it means we are creating I/O load between the nodes because we need to redistribute the data among the nodes. And this actually results in the creation of further stages in the execution plan. Because we need to wait for the other nodes to finish so we can actually get this data. And this is always needed for aggregation of data. And as I already said, so actions will cause an execution plan to be executed. There's a new action, a new job for every new action. And the cluster manager will distribute the tasks among the individual worker nodes. So typically, of course, a single node gets a lot of tasks, right? So because every task is a separate thread. And if you have many cores, you also want many tasks, so all cores have to do something. If you have virtual cores like, how was it called? Like I said, essentially CPUs like this, virtual CPUs, then of course you should also make sure that you give the virtual CPU something to do. So every core should be busy. And until the first action is encountered, Spark will just build the agents. So this is, I guess, a quite nice visualization of this. So you can see here the level transformations, basically just 101. So simple single partition will have exactly one destination partition, and this arrow is the transformation. So this to this. While in the Y transformations, to create this, you have the data from this, but also the results from this partition, but also the results from this partition. Now, if this partition is on some other node, we will have to wait until it has finished, and also we need to move the data to the node where this is processed. So basically this means that the data is distributed between the partitions, and because these are some end-to-end relationship, so that means we create shuffling, so wide transformations, of course, create a much bigger effort for the cluster. And also they mean that we will have the sequence of multiple stages, which can actually slow down the calculations a lot because we always have to wait for the next stage for the first stage to proceed actually. So which can, even the last task needs to be finished before the next stage can actually be started. So that's why we need to make sure that the partitions are evenly distributed, because otherwise if you have a bigger imbalance, then it will become very inefficient if you have multiple stages in the job. Okay, so what's about this execution plan? What does the very first step, of course, is we have this RDB, and we are creating this directed recipe graph out of it. But that's not the only thing which will happen. The next thing which takes place is there's a stack scheduler, which is responsible for the generation of the stages and also their sequencing. So Spark will analyze the thread and then derive how many stages they need and how they must be sequenced. And then there's another scheduler, it's the task scheduler. This one is actually assigning tasks to the nodes, so depending on what nodes are currently what's the busy, so they can take some more tasks. And after this, we have ready to run execution plan for the cluster. And then we can pass this to the execution plan. This will actually be executed. So several steps in this execution plan. And then there are two basically private modes offered by Spark. The first one is the so-called client mode. In this case, the driver runs within the machine from which the application was launched. And it's, I would say, the most straightforward way of running it. So the machine directly communicates with the cluster manager. And this is also the preferred mode for development. So basically, you run the driver runs everything else, and yeah, so everything starts from the driver process, no problem. And then there's the cluster mode. Then the idea of the cluster mode is that the driver will not run on the client machine itself, but it will run on one of the cluster nodes. So the client will send the application to the cluster manager, and then the cluster manager decides to start the driver on one of its worker nodes. So basically you tell the cluster manager, here I have my driver program, now do what you think is the best idea to do. Then the cluster manager will decide which worker node the driver should be run on. And yeah, after this application has been passed to the cluster manager, you can detach your client, so you don't need to maintain a connection with the execution. And that's why, of course, it's the preferred method for production environments. So basically, yeah, you have some kind of decoupling. So once you have submitted the application, you can log out and everything will just continue to run. Because actually the driver is not running on your client, it's running on one of the cluster nodes. Yeah, there are different cluster managers. Actually, there is a standalone deploy mode, which is also some kind of very basic cluster manager. This is what you can use if you are running it locally on your client, because yeah, it's easy. Actually, you don't dedicate, then this will actually be run, so you don't have to explicitly configure it. In this case, but you need to run the cluster manually or via scripts. I mean, if you're running the driver locally, then no problem, right? So because the executor is already running. So, but if you actually want to use this on a cluster, then you need to make sure that there is a compiled version of Spark on each node, because yeah, there's no instance except you that's doing it. So in this case, ensure that you have Spark up and running on each destination node, on each node of the cluster. And then you need not only deploy it, but you also need to run it, of course. So, but of course, if you're running it on a single client for testing purposes, it's a problem, because if you have run the driver, everything else will just run out of the box. Then there is Apache Mesos, but it's kind of duplicated because the last release was 5 years ago, so I won't go into this here. But still, it's being used in some installations, so don't be surprised if you read it somewhere. And it also has some configuration part, which is not available to the other ones, so maybe we will talk about this a little. So just in case you need this, you might need Apache Mesos. Then Yarn, yeah, we talked a lot about Yarn. So Yarn is still this kind of gold standard, so the most common resource manager used for Spark. Yeah, as I said, the basic idea is that we have a separation of resource management and cost scheduling across the different units, and we have a master node which will become a resource manager, and every worker will become a node manager, and then we have a separate application master for each one job of the cluster. So one job corresponds to exactly one application cluster. And then there's also the option to use Kubernetes. Yeah, this basically works like this. So this is the general architecture of Kubernetes. So we have some kind of distributed register, this is TCP, and there's an agent for starting and stopping so-called pods. And a pod is basically it's a kind of container. There can actually be multiple containers running within one pod. And yeah, there is an agent which is able to monitor the resources coming to this cluster. And these nodes are communicating using their own network connection. And if you apply this to Spark, this is used this way. So the Spark driver runs within one pod. and the executors run in driver pods. So every executor gets a separate pod. And if the Spark application was finished, then all executor pods are terminated except the driver pod. So the driver pod remains in the computer state, and the others are terminated. If you know one now what's the best cluster manager, as always, there is not really something you might say which is good for all cases, all these cases, but is let alone in play mode. In flight mode is perfect for local testing because it's simple, because it's a very small overhead, you don't need to configure anything separately, and it's really sufficient for local execution of Spark. So if you're running it on a local machine, use this. It's easy. Then Yarn in either cluster mode or client mode in production. For example, in AWS, still the gold standard for Spark, and also before it was the gold standard for Hadoop, still is if you like to use that for whatever reason. If you may wonder why should I use Yarn in the client mode in production, well actually what you can do is run your driver directly on a slave node, because you can just use a secure remote connection to directly log on onto a remote node of the cluster, and then just run the Spark driver there. And if you're using tools such as Screen, so there's a common Screen you can use in Linux. If you use this, then you can actually discard the connection and later restore the connection. So you can just, it will decouple the output stream from your connection. So you can log onto it, then run the Screen command, and then you're on a separate screen. Then you can terminate the connection after running the Spark driver. And later you could reconnect to the cluster, and then if you just run the Screen command with resume, so I guess -R or something, then it will get back to the output of the driver. So you can actually decouple this. And this is, of course, this is using client mode, because you're already running on the node, so you don't need the cluster manager to move the application to the node. But it's a little bit challenging to do. So, but you can also use the client mode in production, the way as I said. What of course you should do is use client mode, but then run the Spark driver on the notebook, and then not on the AWS cluster, because this would be a very, very difficult, right? Because all the data would be needed to be transferred back and forth via your internet connection. So of course the driver should run within the same network as the other nodes. So make sure that this is the case, of course. Then Kubernetes is an alternative to Yarn in some specific scenarios. So the advantage, or the basic advantage of Kubernetes is that you can move Spark applications around between Kubernetes clusters because they are containerized. So it's actually quite easy to remove. So we can basically remove a running Spark cluster back and forth. So that can be handy in some situations. I can actually, I myself, I can think of so many situations that this is useful, but I guess there are some. Because I guess most of the time you don't want to move around from the Spark cluster. It may happen, So in this case, if you want to do that, then Kubernetes can be useful. However, it has higher configuration efforts, and the resource optimization is potentially more complex because you have the several layers, right? You have these pods and then containers within the pods, and this different monitoring stuff on top of it, which is this database, and everything monitored is built by Kubernetes, and on top there's the Spark instances. So it can be a little bit, more difficult to understand what's actually going on in the cluster. And the problem is that you really need to understand what's going on in your cluster, especially in terms of research usage to optimize the cluster. So I wouldn't recommend using Kubernetes if you don't have a good reason to do so, just because it's complex, right? And always avoid complexity if it's not necessary, because yeah, the one is complex enough, right? So everything which is additional configuration efforts should be avoided if possible. But as I said, of course, there are reasons why you might want to use Kubernetes, or if you really like into Kubernetes and Kubernetes free, and you have a very well thorough understanding of how Kubernetes works internally. This could also be an idea. Okay, now let's look at some further components of Spark. Well, I guess you remember this components image. And yeah, so it's here, so we have these different models which can be used in the Spark. Yeah, first one's Spark SQL. It's a model for structured data processing, and it uses two different data representations. They're called data frames and data sets, instead of RDBs. So basically, well, instead is a little bit misleading because they're actually working on top of RDBs. So internally, we are always converted to RDBs, but it's working on top of it, so it's an abstraction on top of RDBs. And they have more structured information, which can be quite useful. And the structured information is used for optimization. So Spark is able to optimize the queries based on the structured information. And you can execute SQL queries either natively or on type databases, and then return data sets or data frames. And the SQL interface can be queried by the code line or via JDBC. And then this is actually the optimizer pipeline, so it's the Catalyst optimizer. Yeah, and you can see that either an SQL query or data frame, which is basically the same, will go into a logical plan, plus the unresolved logical plan, and then there is an analysis going on, which will lead to the logical plan is resolved. And yeah, after some logical optimization going on, we have an optimized logical plan. This will then be transformed into several physical plans. And then there is a close point applied to the physical plan, so then finally Spark will select the physical plan as the best close model. So it's then writing different plans and then looking at the best part of this. And then finally, this will lead to a quick generation and finally we have So you see that it's quite a pipeline that actually comes from our data frames to the RDBs. And the operations on the RDBs are already here at the end. So if you're working on RDBs, then you are somewhat working a little bit more around the machine room. Yeah, of course, it can be useful that Catalyst is able to optimize the graphs based on your operations as well queries. Then there is MLlib, which is as the name implies, it's a machine learning library. There are APIs available for Java, Scala, Python, and R, so basically it's for languages which are mainly supported by Spark. But there is also an integration with NumPy, different R libraries, and also any Hadoop data source, such as HDFS, HBase, or local files. And it has some nice algorithms, some of which you have already got to know. So, like for scalarification algorithms for logistic regression, APIs also can use the regression, decision trees, random forests, also lots of clustering algorithms, k-means, Gaussian mixture models, which is basically weighted sum of Gaussian functions, and of course many more. And some workflow utilities, so it offers feature transformations for normalization and hashing. You're able to construct a machine learning pipeline, so it can define different stages in the machine learning process. And it also offers a persistent management of machine learning models, so loading and saving models and pipelines. And also some stuff on the linear algebra, like PCA, so principal component analysis, and various statistical methods. So lots of stuff related to machine learning can be done with this library. Then there's this GraphX, which is an API for graphs and graph kernel computations. And you can use it also for data visualization of graphs, any kind of graph transformations, and also iterative graph algorithms, which are customizable. There are many built-in graph algorithms, but be careful because officially it's still in the alpha stage. And yeah, as I said, it might work, but maybe it might also not work. But to give an impression, what are the graph algorithms here? PageRank was the original Google algorithm for ranking search results. Basically, the idea of PageRank is that a site is ranked higher if other sites are pointing to this site, and the others, depending on how ranked these other sites are ranked. So that's the basic idea, but of course, the current Google algorithm is much more complex, and they're also not really publishing it, so no one really knows except some guys at Google. Then you can also have graph interconnections, label propagation in graphs. It's finding the so-called community structures. So these are community structures. So basically, these are regions of the graph which also have a high degree of connection within the cluster and a small degree with outside of the cluster. So the clusters are only connected to single regions to other clusters. We also have the singular value proposition. So the idea is that you can represent the matrix as the product of three special matrices. Something you might have heard of in the algebra lecture. I don't know, quite common procedure. So-called strongly connected components. These are subgraphs of the directed graph, in which every node is reachable from every other node. So like here, so these are strongly connected components. And as you can see, so here, every node is, if you're just looking at this part of the graph, so every node is reachable from every other node, but not outside this subgraph, the same goes with the subgraph. And also something like the number of triangles in the graph, so I guess, get the idea, so lots of graph stuff. And actually, well, even though they call it alpha, I played around with it a little, so it seems to work quite well. But as I said, they call it alpha, so be careful. Then there is structured streaming. And what's the idea of structured streaming? Basically, it's a scalable and fault-tolerant stream processing engine which is based on Spark SQL, so it runs on top of Spark SQL. And you can formulate streaming calculations similarly to batch calculations, because they're actually under the hood. It's implemented as a micro-batch engine. So it's just running batch processes repeatedly. It of course utilizes the dataset DataFrame API, since it's based on Spark SQL. And it can actually achieve end-to-end latencies down to 100 milliseconds, which is quite good, I would say. And there's even a low latency mode, which they call continuous processing. And in this mode, you can get latencies as low as 1 millisecond. But of course, less than some drawbacks. That's why there's a separate mode for this. But without restrictions, you can have end-to-end latencies down to 100 milliseconds, which is also quite remarkable. How does this work? So the idea is that incoming data of your data stream is appended to an unbounded table like this. So if there new data, we have just infinite many rows being added to this unbounded table. So it's bounded with respect to addition of rows. And now you can define a trigger, and the trigger could be like every 1 second. everything a second. Of course, it could be like every 2 seconds or every half a second, maybe. And yeah, as you can see, this would be our input table. So of course, it grows as the number of rows are appended. And then our query will actually be rerun every second. So the results will be updated with respect to the new incoming data. There are several modes for the output, but in general, the result will change as with respect to the new data. And there are several output modes. First one is the complete mode. In this case, all results are linked to the external storage. Then there's the append mode. In this case, only newly arriving table rows are written to the external storage if existing rows are not affected by the processing of the new ones. And finally, there's the update mode, which only writes table rows to external storage that have changed since the last data. So the update mode writes the least number of data, and the complete mode writes the biggest amount of data, of course. And now we can see like an example how this behaves. So let's see like if we have first we have this cat dog is approaching, then there's another row dog, yeah, and T1. So our first second. So now we have our input table, and it has cat dog and dog. And then if you had a query which, for example, would do a word count, then it would counter, okay, we have 1 cat and 3 dogs. Okay, so this would be written like to external storage. Now, in the next second, we have old cat incoming, our screen. So now it's appended to the table. And yeah, actually, it doesn't necessarily, it needs to arrive exactly at t equals 2, but it just until then, yeah, it will be appended here. So everything which arrives between this and this time stamp will be appended here for t2. And then, yeah, so we now have old cat, and now our query is run again. And you see the query now counts that, okay, now we have 2 cats, still 3 dogs, and also an owl. Yeah. And then, yeah, there might be another dog and another owl arriving in the data stream. Now we see our table grows. And then the query is again rerun, and now we have 2 cats, 4 dogs, 2 owls. So I guess you get the idea. So basically, you can rerun the query on a trigger, based on the trigger, and it will update the result based on what has been changed on the table. And you can also define a sliding window like this. So a sliding window basically means that you're looking at some period in time, and the analogy is that you have some kind of window over the time, and then you're moving this window around, right? So that means that data are not directly vanishing, but more like aging out, out of the window. So, and then, for example, so don't confuse this with your triggers, because a trigger could be like 5 minutes, for example, but if you're sliding window size here, which is a 10-minute window, then, if, for example, here we have cat dog arriving at 12 2 minutes, then 1 minute later dog arrives. So now in our first trigger we have this in the first sliding window. So these are, of course, it's the word count, so the result of the query. And then another data point arrives sometime later, and now you can see, okay, the query regarding this window has this result. But then there's another window like, it's shifted by 5 minutes, but still 10 minutes long, right? So that's a different content because what has arrived before 12 or 5 is not contained in this window. And then again, even further 5 minutes later, there may be some other data points arriving. And now you can see, okay, now we have 3 different windows, and the results of our query are different depending on the window we're looking at. So the idea of sliding windows in general is that it's it's smoother than just abruptly discarding old data and taking new data into consideration, right? Because you have data that is kind of aging out, and new data is arriving. So very often sliding windows are better than just random sampling of data. So this is a small usage example for the Spark Streaming API. Like this. So here we could read input lines from local host as a stream. In this case, here we just need to open a socket. So basically, it's a socket on the local host, and then connect with it and just key in some data, and then so our Spark Streaming driver is decomposing the lines into words like this. About the encoders, when we're talking about this data. So for the dataset API, you always have to define encoders for serialization, deserialization. So the lines are split into words. Then we will create a continuous word count, like this. So we are using this with by and counting it. And now we are starting a continuous queue like this. So here we define an output code, the format, and then with await termination we will run the Spark Streaming, and then it will just, I guess the default is like 1 second, but of course you can adjust the frequency. And it will just permanently, every 1 second it will be executed, update the output, and give you another output until the word ends or until it terminates. Whatever comes first. You could test it like this. So you could connect with Linux console tool like Netcat to this TCP socket, and then we could just key in some words. And now this, our streaming program will connect to this port and then look what's incoming, and then start to count the words as they are. As you key in some more words here, every second you will get this output. The table also will be updated. So I guess pretty straightforward actually. So that's it. So now I guess we have a break, and then we look at the exercise, and in this we will actually be preparing the IDE and actually running Spark on your local computers.
Thank